Now let us understand what is happening with a car that is moving on a road. So here I have shown two possible views. So the right hand side view here is the top view. So the car is moving along a circular path on a road. Like I told you earlier, the car cannot turn if there is no centripetal force. So let us say if the car is moving along a circular path, even if the path is not exactly a circle, we can instantaneously consider it to be a circle as the car is turning. Now let us say that the car is turning and it has an instantaneous turning radius r. For any particular turn at every moment, we can define a radius r, that is the radius of curvature or radius of instantaneous curvature of the path that the car is taking. So let us say the car is turning over here and the instantaneous radius of the turn happens to be equal to r. So this is the radius r that is shown. Okay. So there is only one force, namely the friction force from the ground, that is going to be able to supply the centripetal acceleration, because there is no other force in the horizontal direction. So to illustrate that, we have this adjacent diagram drawn towards the left, and herein we understand that this particular force is nothing but the normal reaction, and this particular force is the gravitational force. So mg and the normal reaction will actually balance each other out. We would like to find out in this particular scenario what is the maximum velocity with which the car can turn without skidding or without slipping outwards, basically. Now when we say that the car is going to skid with maximum velocity, it becomes imperative for us to use the maximum value of friction, and the maximum value of friction possibly can be mu n, where mu is the coefficient of friction. Here we are assuming that the coefficient of static and kinetic friction are the same, so mu happens to be the common coefficient of friction. So mu n is going to be the maximum value of friction. If static and kinetic friction are different, then we would have had to use mu s into n, wherein mu s is the coefficient of static friction. But here we are assuming both of them are the same. So mu n is the maximum frictional force that can apply in the horizontal direction towards the center. So this force of friction, okay, this force of friction, which I'll now denote, this particular force is going to be equal to mu n. So this is the maximum force of friction. I repeat, the reason why we are using the value of the maximum force is because we would like to understand what is the maximum velocity with which the car can turn over here. That's what we would like to understand. Alright, so here we get mu n, which is towards the center, the only force towards the center. This is equal to mv square by r. Okay, so this is going to give us the max velocity of turning. If we were not to find the max velocity, then we'll simply get friction is equal to mv square by r. Let us say the car is moving with a lesser velocity than the maximum velocity and it's not skidding, so friction will be provided as much as is required for the car to turn. So this value of friction can be anywhere between 0 and mu n. This is the normal case, wherein the car is not turning with max velocity but rather with a velocity lesser than the maximum possible velocity. So mu n over here is equal to mv max square divided by r. And since we know that n is equal to mg, we can thenceforth write mu mg is equal to m v max square divided by r. So if we just cancel out the m's, we get v max square is equal to mu rg. Therefore v max is equal to under root of mu rg. Alright, so this is the particular value of the maximum velocity with which the car can traverse a turn without slipping outwards. Now there is one interesting phenomena that happens as far as rotational or rigid body dynamics of the car is concerned. If we were to consider the car as an extended object, then in this particular scenario, a phenomena is going to take place. It is called as the shift of normal reaction. Let us say if we are analyzing this particular tire, or there are 2 points of contact over here, let us say C1 and C2. Let us say we are analyzing the point C2. Okay, so with respect to the point C2, with respect to the point C1, there are 2 normal reactions that consist of the normal reaction N. Okay, there is this N1 and there is this N2. Alright, so the normal reaction that was shown over here, N, this normal reaction is going to be consistent of N1 and N2. Alright, so we can understand that N1 and N2 are going to be different. Let us see and understand why and how. Alright, so this is the mg that acts in the downward direction. So if we are to balance the torques, okay, if we are to balance the torques, then in that particular case, if we, let's say, analyze around the point C2, then in that particular case, let us say the outward force, right now I am analyzing from an accelerated reference frame. So instead of using the centripetal force, I am going to use the pseudo centrifugal force. So the outward pseudo centrifugal force, which is the car is being thrown out, is mv square divided by r. Here I am assuming familiarity with the concept of centrifugal force. Mg is the downward force. Let us say b is the width of the car. B is the width of the car, let us say, and h is the height of the car. Let us also assume that the center of mass is at a height of h by 2, and the center of mass is also at a height of b by 2. So the car is more like a uniform block basically. So we can understand that the clockwise torque about the point C2 is going to be, because of N2 is passing through the point C2, so N2 will not give any torque. So N1 and mv square by r are the 2 points that are going to give torque. So I can note that N1, okay, into B, so that is force into perpendicular distance. So this is the N1 force and this is the perpendicular distance. So force into perpendicular distance, N1B minus mg into b by 2. So mg into b by 2 is trying to turn the car in counterclockwise direction, or rather trying to prevent the clockwise overturning of the car. So mg into b by 2 will have a negative sign associated with it, plus mv square upon r into h by 2. So this is mv square upon r into h by 2. So this is the net effective clockwise torque. Okay, so this net effective clockwise torque will be balanced out because we are assuming that the car is not overturning. So this is going to be equal to 0. So from this particular equation we get N1 to be equal to mg by 2, rather minus mv square upon r into h upon 2b. This is what we get N1 to be equal to. Now in order to find out N2, it is better to write equations in such a manner. So these particular equations were written around the point C2. So this analysis was around the point C2. Okay, so if we do the analysis around the point C1, then this is the point C1, then we get that mv square by r and mg, these two are trying to turn the car clockwise, whereas N2 is the only lone force that is trying to turn the car counterclockwise, or trying to prevent the car from turning clockwise. Again, since the net torque is 0, we can then write N2 into B. Okay, so this is this kind of torque. N2 into B is this torque, So I'm writing down the equation for this kind of a torque over here, and hence this is a counterclockwise torque, so I'll get minus mg into b by 2 minus mv square upon r into h upon 2. So this is the net torque, which happens to be 0. Therefore, from this equation I get N2 to be equal to mg by 2 plus mv square upon r into h upon 2b. So here basically we are getting a positive sign with respect to finding out N2, and we are getting a negative sign while finding out N1. So we can see that N1 and N2 are not the same. In fact, the difference of N1 and N2 is the reason why the car is not overturning actually. So there is something called as shift of normal reaction. So the net normal reaction is not necessarily passing through the center, but whereas this net normal reaction is shifted towards the right. We can easily realize this phenomena because being human beings, we are experiencing mechanics on a day-to-day life basis. So if we are running very fast, let us say, and if we want to turn towards the left, we are running very fast and we want to turn towards the left, but we want to do it in a very small radius. So we want to quickly turn towards the left, like we don't have enough time. Let's say we are running in a narrow corridor and we don't have enough time and space in order to turn left gradually, unlike running on a ground. Then what we would have to do is we would have to put some pressure or force on our right leg in order to break our speed, and then we would have to stop and then turn towards the left. So it is understood that we are increasing the normal reaction on the right leg and decreasing the normal reaction on the left leg as we are turning towards the left. Similarly, here also the car while turning towards the left. So the path of the car, mind you, is like this. So while the car is turning towards the left, the car also has to put more pressure or force towards its right hand side so that it is able to cope up with the left turn. From day-to-day life's intuitive understanding of physics also, this is pretty clear. Alright.